Howard?
Yes, I'm Howard Gordon. I worked for 44 years at NSA, and now
No
I'm
such
retired.
agency.
No such agency. National Student Association.
Never say anything.
Yeah.
No such agency.
Okay. Don?
Yes, I'm Don Lavani. I'm retired from the National Institute of Standards and Technology.
Okay. Satya?
Yeah, this is Satya. I'm a plasma physicist by training. I worked at SAIC mostly as a contractor for NRL and NASA. Now I'm
You
retired.
want to click your camera on?
Okay. Let's see, how do I do that? Let me see.
Lower left corner, there's a start video button.
Okay.
Let's see.
Okay. Our speaker today is Bhagarath Joshi.
Jerry didn't have a chance to introduce himself.
Oh, I'm sorry.
I'm Jerry Stenbakken, also retired from National Institute of Standards and Technology. Thank you.
I apologize, Jerry. I didn't. The pictures keep moving around. I didn't mean to omit you. You're a valuable member of our group.
Thank you.
Okay. Trying again. Our speaker today is Bhagarath Joshi. He received his MSc in solid-state physics from the Gujarat University in India, and afterwards studied at Boston College and the University of Massachusetts in Lowell, where he was awarded an MS in computer engineering. He's a consultant to the computer industry and has pursued theoretical work in nuclear physics and submitted a paper to Nature. And today he will tell us about the excess neutron shell model to explain stable isotopes and the non-existence of stable isotopes beyond atomic number 83. Joshi.
Hello, everybody. I didn't work for anybody, so that's I was a consultant all along, so that's my story. Here, I'm going to share the slide. Okay, there we go. Now you see that little picture here. It's an excess neutron shell model of nuclei, and the blue area. This is just to give a, it's like a peach where you have a soft, nice, nutty thing in the center. So that is what I'm trying to show. And the blue area is just the empty space. And the red area, that is red circle that you see, that is the p-n shell, which is made of protons and neutrons. Where p-n, proton and neutron, they pair up. But before we go to that, I want to do this in two parts. My major goal here is that everybody is listening here, maybe, want to do some further research, because there are so many elements and there's a lot to do over here. So I will go in a very, so that everybody can understand. Okay, this didn't go. Okay, I got it. Okay. Here is the periodic table, and when you look at the periodic table, there are only 80 stable elements. Even though the technetium and promethium, they are not very massive elements, they are unstable, and none of them exist in the nature. They are only made in the nuclear reactor through other fission products. There's stable elements that can be also made unstable, and that everybody knows about it, that you throw the neutron at it and or remove one from it, and it will become unstable. Now this last thing is just the haha. There is no hydrogen isotope with more than three or more than three neutrons or three or 100 neutrons. So that's what the whole idea is. So there is a summary paper that is with MIT. They talk about the statistical feature of the thermal neutron capture cross sections. And in that one, you can read also that very low energy neutron capture cross sections are important in the different processes. And they also name it that ultra cold neutrons, even 0.001 eV, they get captured. Now for capturing, we need the resonance. Without the resonance, it cannot capture anything. And so that is my whole goal, was why they are saying this. And also there is a whole book by Flashback and some another guy there, which says that there are simple doorways in the atoms for nuclear capture, neutron capture. So that is, interesting. And we look at this traditional plot where all the elements, isotopes of the element, radioactive or none or otherwise, all of them are plotted, and then it says Z equal to N, does not give us much idea on what is going on. So as a result, so what I did was I said that this is my preparation to take you to the shell model. So then I said that, okay, let's look at all the stable elements. This particular plot is very, very important, where I said, okay, let's look at odd Z elements, because odd Z elements always show either one stable isotopes or the one which is close to one, and then there might be one or two other ones, but which is very minuscule amount. So when I said that the probability of this odd Z elements having a stable isotope is only one, and that is a one because there's only one abundant isotope in the nature. There is no other. So now when we look at all of them, you can see that 43 right here and 61 here has no stable isotope, so that it's not, but every other one is either close to one or they are one. So this is very interesting thing. Now if you look at the even Z, even proton isotopes right here, and they are all stable isotopes, you can see that, let me show this, it has more than one isotope. This says number of stable isotopes, and it has more than one. Like if you take the element 50, which is tin, then it has a 10 stable isotopes. Total, becoming the total abundance being one. So that is what is happening. And now also you can see this in a particular plot, that the normal wisdom is that, if 50 at 50, if it has 10 isotopes which are stable, then it should keep going with higher elements, but that is not happening. You can see that all of them are going down. Now this is just the fact that I have, which is experimental fact, and it is available to everybody. So as when it becomes 82 right here, you can see that it has only 4 isotopes which are stable. But when it is 50, you can see that it has 10 isotopes. One also other thing you can see that just by plotting this way the data, we can see that which elements will be good, element isotopes will be good as a neutron absorbers because it has more stable isotopes, and when it absorbs the additional neutron, they can go to the certain level which shows here that will be stable, because in case of tin, but we is 10 isotopes which are stable, and 48 is cadmium, which we normally use in nuclear reactors to control the reaction, which has 8 no 6 actually, yeah, 6 isotopes which are stable. So tin is a better neutron absorber just from looking at this but we use, I think, cadmium because of the melting point issues. Now neutron, it is a neutral, and so it should be able to lump together with other neutrons and become one solid neutron, but that's not it wants to be with a massive neutron, but it doesn't want to do. Every neutron wants to keep their own identity. So that is another question that is going on in my mind, why it's doing that. Now recently, there are some experiments are being conceived where they want to find electron no electric dipole moment of neutron, and I think that's being done in CERN. So nature prefers stable systems, so the probability of stable system goes with the abundance. If it is more abundant, and if it is only one, then that is the most preferred state of that particular element. So from this point, I said, okay, it is getting, we know all this. So let's look at closely some of the isotopes. These I have picked up 3 elements. One of them is platinum, another is gold, and another is mercury. Now, if you look at platinum has 6 isotopes with various abundance, as I have relative abundance that I have put together. With this total combined is 1. But the gold, the next one, which has the Z79, 79 protons, that has only 1 stable elemental isotope, only 1 stable, and which has the total abundance of 1 with 79 proton and the total and 118 neutrons. So that is the only one stable. Now you go to the next one, which is mercury, which is only different, which is a even one, and you can see that there are 7 isotopes which are stable. All of these totaling 1 here, and this is 1. When you add all the relative abundance, it's 1. So now the question is, what is making it so that the gold has only 1 stable isotope while the neighbors have more than 1. So the difference that you see here is nothing but the number of protons, the Z number. If you have 78, it has more, 79, 1. So that way, if you have say some new element that you are trying to cook up in the lab, and you say, okay, it's going to be 199, then it will have only one possibility to make that isotope. But if you are trying to make the 200 one, it will be, albeit, it will be radioactive ones. But if you do 200, then there might be more possibilities of making that radioactive for 200, Z number 200, as opposed to 199, because it has only one and you might miss it and you might take longer to figure out how many neutrons I need there. So this is where, so I said this is interesting. So let us see now. Let's get now before even we go there, here it is. So this is the stable, this one here, right here is the stable isotope of gold. But if you just have one more, then it right away disintegrates. There's another one, if you just have one less, instead of 39, you have 38, it disintegrates right away. So something is happening. And from this picture, the few slides, it is understood that looks like that there are two different mechanisms are happening, and two different mechanisms are giving stability, like one for odd Z and one for even Z. So what is it? So I said, let's look at the quantum mechanics and let's see if quantum mechanics can help us. So here it is the, time independent Schrodinger equation. And we are investigating the quantum particle in the gravitational field. When we solve this for n equal to 16, you will see that we have levels. The blue one is a classical, where it says you always have a resonance for some reason, but when we do the quantum, it gives us levels, different levels. So what it is trying to say that neutrons will have some sort of levels that we can use. So I said, okay, and we created that. So I said how it would work, because we need some stability, and spin is this. So there was a center where, one particle can stay, because you have the possibility of a standing wave there. And this is just the simple, the shell model, which I have adopted, except for this particular F. F is the first neutron. If you have any excess neutron, then the first neutron will go there, where excess is Z, atomic number, say total number of neutrons in the system minus the its element number Z. So that would give us the excess electrons, because that many excess that many excess neutrons are needed for us to make that system stable. So this is, so here, this is, we are revisiting this, where you can see that there is a one neutron is in the center, and the rest. So this looks like a peach, and outer shell is a NP shell.
Hello?
That is because the experiment has shown that neutron and proton, they stay together in a orbit. So that is why that is the NP shell. So now, so this is my model. So I apply this model, and that this is how this particular one is the ordinary not ordinary, but this is the NP shell levels, you know. This is a 1s and 2s, 2p. Similarly to that, there is no F level here. The reason for that, there is no space to put the F. Here we have, you know, so looks, the whole nuclei now looks like a planetary system with F in the center, the first neutron, if there is in excess. If there is no excess, then you don't need to put anything there. But if any excess goes to the, you know, just like the sun in our orbits. And when you go up and look at it, now you can see that this matches, and in words, if you I'm trying to say something. So if you look at that, the 4F in the NP shell has 5 NP pairs, and here in 3D shell, you know, this follows the normal packing order for the, you know, for the shell. And that is what I have done here. So then the from this we can deduct that spin of the whole system is 3.5, because this is 2.5, and here we are getting another 1 from this excess neutron cell. So total is 3.5, which matches with the experimental results. Now, I did, you know, further study and found that the for this element to be stable, it has to balance somehow the Coulomb forces with the gravitational forces. Otherwise, and that is a part of the initial condition. If that initial condition is not met, elements don't form. So that is what it is trying to say, that this is a, you know, simple our classical equation, and this is a gravitational equation, and n minus p is the excess neutrons. And if this value is less, then it will form in certain cases, but it will be a positron emitter, beta plus. And if this value, the Coulomb forces are less than this gravitational forces inside, then it will be beta emitter, beta minus emitter. That means it will release the electron. So in one case, the proton will give up its positive charge and turn into neutron. And in the other case, neutron will give up negative charge and will become proton. So that is the difference. So either it will, you know, in terms of if you will look at the gold radioactive isotopes in gold, if it has a less, that means less than 39 neutrons, then those will be all either be emitting the positrons, or if it has more than 39 neutrons excess, then it will emit the negative charge, that is you know, electron. So and it will convert into mercury. The other one will convert into platinum. So that is the situation. Now here M is playing a part, and that is where the excess neutron shell model comes into picture. Now, Dr. Einstein, you know, Albert Einstein, he taught us how to do some thought experiments. And when there is absence of the real experiments, he resorted to, thought experiments. So now you can see that, for gold to be unstable, you can look at it, when the gold is getting its stability from the excess neutron shell model, excess neutron shell. On the other hand, platinum is getting its stability from the NP shell. So it is a Coulomb forces, and internally they are quite able to, handle any changes in the, some changes, not, I wouldn't say any changes, but some changes in the neutron shell. Now, when you look at the neutron shell, it can take additional neutrons and become, and it has resonances, which I showed you in the plot here. See here, there are resonances. So those ones, so it can take, but when it is a odd Z element, then it cannot accept any more neutrons, because that is the only stable, one stable element. So when the next one comes, it cannot, the excess neutron shell is not a spin balanced one, if we look at it. So when it is not spin balanced, it's going to destruct the whole system right away. So looks like from my analysis that spin is quite important in element formation also. So whenever spin is balanced, say in terms of NP shell, then it can take more neutrons and remain stable, or take less neutrons and remain stable from the ideal position. But in case of, odd elements, because they are getting their stability from the neutron shell, which as I have shown, it goes out of balance right away, and spin is not balanced. So when spin is not balanced, the whole inside goes haywire and does a destruction, and it becomes radioactive. So this is the, main phenomena where spin is not balanced. So as you go further, here I have one more aluminum, which is 27. It's a 13, 13Z, and you can see that it has more stable. It's only one. Oh, I just lost it. Okay, it has only one isotope which is stable. Which can be, plotted using, the labels can be plotted using the and here this one is tin, and in tin you can see that there are 10 different isotopes which are stable. So it can take more neutrons in the neutron shell, and still it becomes stable, stays stable. So this is the thing. So from there, we can deduct that why all the other elements which are, higher than Z83 are radioactive. It's because the excess neutron shell is so massive that there is no space for NP cell to survive. It always continuously does the destruction. and it becomes radioactive because there is the gap between the excess neutron shell and the NP shell, the beginning of the NP shell inside is so small that it cannot withstand the destructive forces of the neutrons inside neutron shell. So there is a constant collision going on, and that might be the reason why the alpha emissions, where helium particle is thrown out, is because they might be forming the local groups there, and that local groups, once it solidifies, it's out to the door. Now, one more thing that I'm working right now on it is because of the excess neutron shell is so massive, and the gravitational force, even though it is a very little, it still, when you look at the dimension, the dimensions of 10 to the power minus 19, and also from the other paper where they are saying that even if it is a minuscule forces, they are taking toll on the elements. So that is the thing. I may not be able to be so sophisticated in saying things, but that is what I try to convey. The other things that I am trying to understand is that why all the radioactive elements are not disintegrating at the same time, and there is a half life. For that, we need to do the many body uh, solutions, and in that one, what happens that we can approximate by using the quantum mechanics, and the in the word I'm looking for is we can put Schrodinger's equations in a periodic potential, gravitational potential, and that can be visualized in the solid. If you have a solid, all the elements are in different, in regular space, and then you can put that Schrodinger's equation in a periodic potential, gravitational potential, and try to understand that why the radioactivity, that work is still going on, that why all the atoms, atoms are not disintegrating, radioactive atoms are disintegrating at the same time. So that would tell us and give us the idea on some half-life. So that is my idea. Now, I don't know how much. It's only been half an hour, and I am at the end of my presentation. One another thing, I'm going to make some bold thing, that spin balancing gives the stability. And one thing that comes out of this, that when the Big Bang occurred, all the elements were formed at the same time. That is one of the bold statements that I'm trying to make. And the reason for that is simple. If we look at the state of or just the visualize the state of the matter at the time of Big Bang, it was nothing but a huge blob of whatever the material was, and mostly it should be neutron. And even in the for low energy uh, fusion, you can see that if you have 4 neutrons, they will fuse easily than trying to fuse to deuterium, the hydrogen atoms, because what neutron does not exist in the nature outside the nuclei. Only place that they exist is in the nucleus, and if they come out of nucleus one way or the other, that they're gonna disintegrate in 10 to 15 minutes into hydrogen. So when the Big Bang occurred, according to me, okay, not anybody else, but at that time, all the elements must have formed, because it is the easiest and simplest way they can form. Because in the first 15 minutes of the Big Bang, there would be a lot of hydrogen atoms. And while all those things are forming, because any neutron escaping from that is going to be disintegrated into hydrogen. And similarly, all the other neutrons staying together while they are disintegrating, depending on their half-life, it will form different elements. So that's what I wanted to say. So that's the end of my presentation. If there are any questions, I can answer that. I hope there is some information that can be utilized. Yes, sir.
Yes. Tell me a little bit about the virtual electrons and positrons. What can you say about them?
Well, what I would say is virtual electrons and virtual positrons, they are the mirror images, basically. If you take a, virtual electron, since it is virtual, according to Einstein, we don't have to dwell on that too much, but, it is, I don't know much about it.
Well, how many can we have in, say, in a proton or a neutron?
What?
They're associated with protons and neutrons, right?
Yeah.
So how many? I calculate that that every shell, diameter d shell has 2d squared positions for an electron or a positron. And that if you combine an electron and a positron, you get a boson. And so it doesn't act like a fermion, but its components do. And if you have a diameter 30 shell, you can have 900 positronium bosons in that one shell. And that accounts exactly for the mass of the proton or the neutron. If you take the mass of a proton and subtract the mass of its components, you get 900 times the mass of a boson, of a positronium boson.
I understand that, but my thing that I did, the research involved only the three basic particles, electrons, neutrons, and protons.
Well,
Because that is where I wanted to stop, not go beyond how many positron or other things, because one positive
where does
charge would be one and negative charge would be one. That is
where does the
electron
hadron get
charge.
its mass?
Huh?
Where does the hadron get its mass? A proton or a neutron? I claim that it comes from this positronium shell, and
No, I
that
understand
shell
but
fills the entire surface area of a diameter 30 shell,
yes,
and
but see,
that's why a proton or neutron acts like a fermion,
Mhm.
because its
That-
components can't be in the same place.
Mhm. that is deeper into the particle physics. What I was going with is the accepted value of the mass and accepted value of the mass of the electrons, neutrons, and protons. That is, and the weight, which will create the gravitational field, gravitational pull. So that is what I was going with. That the other thing is, it's like that um, when you are accelerating, some particle and breaking them up and looking at it a different way. So what I wanted to do is go back to the fundamentals here and not go beyond too deep into the particle physics. So for
Well, I
the
wanted to
reason
go too
is that,
deep.
sometimes when we see something you are accelerating at very close to the speed of light and then smashing the two particles, and then you are looking at, but what happens that the mass created will also be that value of the c that it has accelerated to. So that value also needs to be added, and that can give us some more values than we need to look at it. The if we can just take a knife and smash it, that's because our way of smashing is by accelerating at a very high speed and then smashing them together. So that acceleration and the energy that we put into that system will also convert to the mass for a split second. So it gives us some different values here. But the neutron that I have envisioned is like a small capacitor where there are two charged particles, one is positive and the another is negative, and right in between is a dielectric. Now that one, you can, with three quarks, that can be, uh,
Well, my calculations shows that a hydrogen atom is totally balanced between matter and antimatter. You add them all up, you get zero in terms of charge. But you get
the
a mass.
antimatter and matter, I haven't done any study on that. No.
Well, thank you.
So matter and antimatter is altogether different issue. When Einstein, was working on some of the equations, he discarded the negative ones, saying that that's not physics or something like that. So negative results are sometimes misguiding. That's why he
Okay.
discarded some. So assuming that he was right, you know
Well, we can work entirely in terms of positive charges and still get the same things.
that's true. No, we have the negative and positive that charges.
It's more
But
like a balance.
in terms of matter, it's questionable. But and we are still doing the study on that. We cannot just say that exists.
If you have a tire on a wheel and you balance it, you put weights on one side or the other or both,
Yeah.
so that it spins smoothly.
Mhm.
Now, that does not mean that the ones on one side are the negative of the ones on the other side. It means they're balanced, and that's all it means.
Right. No, I understand. But my goal was here to introduce the neutron shell and how it came about for me, and to show it to everybody that is the one where spins are not balanced, then the uh, possibility of element is not there. The element will not exist. So for element to exist, the spin needs to be balanced. So in case of gold, the gold is getting the stability from the excess neutron shell. And in case of platinum or mercury, it's getting the stability from the PN shell, as I proposed. So those two things that I wanted to point across. And in getting the stability in excess neutron shell, in the center, there is a one, first neutron of the excess has to go there. And that creates a one little standing wave if we go look at from the quantum mechanic perspective. And the remaining forms the shell. So those are the two things that I wanted to show. And just by rearranging the looking at the periodic table and all the research done so far, we can see that there are two different mechanisms for the stability of the isotopes. If it is a even Z, then it gets the stability from NP shell. And if it is odd Z, then it gets the stability from neutron shell. And since it's getting from neutron shell, it has only one possibility, and there is only one stable isotope. So that is the only thing I wanted to point out.
Joshi,
I would,
hello.
Hello.
You commented on all of the elements being created during the Big Bang.
Yes.
And I'm not sure if you're implying then that the current abundance that we find in nature then is a result of the decay of all of the elements from them. But also stars make elements.
That is true. Yeah.
That would affect the relative abundance of the elements that we see, was how recently we emerged from a star exploding.
Yes, that is true. The that will be the if unless the star explodes, the distribution of the universe in terms of elements will change. So star needs to explode and share with other stars or other in the universe. But Big Bang shared everything with every planet. So if we go to Mars and do the abundance analysis, I am sure we will find the similar distribution like Earth. Or if we go to some another, say Saturn or one of the moon of the Saturn and do the analysis, we will have the similar elements.
your theory should explain why there's no hydrogen 5 or helium 5. We have helium.
I didn't get
helium
it.
3 and helium 4, but no helium 5, and I think that's because the neutron shell is full.
Yes. No, actually, there is no gap between, because if you just look at in terms of classical, the center of gravity keeps on lifting, but it also does the pull. It pulls on the NP shell and makes it smaller and smaller. If you introduce more neutrons, it will make that shell smaller and start the neutron shell will start interfering with the NP shell and make it a destructive completely. So there is always an upper limit.
That's why there's no helium 5?
Yeah. If you just do the thought experiment, you will know that that, there is a pull going on between this NP shell and the electron shell, and it's going closer and closer, and then there is no way it can stay, because everything is rotating inside, or we from quantum mechanics perspective, those are waves inside, but in reality, there is a mass also going on like that, and that will destruct it. That is why, uranium, we don't have a stable uranium. We always have a radioactive uranium. All the isotopes exhibit radioactivity, because the neutron shell is so massive that it will interfere with the NP shell. The gravitational pull inside, it's like huge. Anything?
You answered my questions. Thank you.
Thank you.
Thank you for a very interesting discussion.
Thank you.
Talk.
Thank you very much, Jerry. This work requires even more work with the solids, because it is in the solid state physics, we look at all the elements and solids, and we find that the electrons of the valence electrons, they behave as a cloud. So you cannot tag which electron belongs to which atom inside the solid. So similarly here, when we look at the neutrons, they are also untaggable, because neutrons can go from one to, and then in the recent experiment at CERN, they have found the neutrons outside the center of the element. So they were outside the element. So that is a new, last year or the 2 years ago, they did some experiment, and they found that the neutron was getting out of the system completely and still bound with the element. So if that is the behavior of the neutron, then when you look at the solid, in solid, the neutrons from one system to another system might be moving, one nuclei to another nuclei, and giving temporary stability. So that is the reason, that temporary stabilities that system gets might be giving the rise of the half-life. So all elements do not descend, all the isotopes of the, say, radioactive isotopes disintegrate at the same time of the same element. I mean, say if you have a uranium-235, they don't disintegrate at the same time. So that may be the reason, because in the periodic gravitational field, they might be moving around. So that is a possibility which needs to be investigated. Anything? I have, given a lot of, bold statements here, but those still needs to be investigated, and we can, I am still continuing with that many body problem of Schrodinger's equation in a periodic gravitational potential, and want to see how, what answers that will give me. The one thing that if you try, just to satisfy the curiosity, the spin calculations comes out correct when we arrange it like that of the element, stable elements.
Okay.
Okay. I say again, thank you for an interesting talk. I was
Thank you.
going to announce that in November, on November 17th, Steve Obenshain from the Naval Research Lab will talk about high gain inertial fusion. We don't yet have a speaker for December. I tentatively have think that Jim Drake from the University of Maryland will talk about magnetic reconnection on January 19th. Rudy, have you had a chance to
Not
contact
yet.
Scott Shepard?
Not yet.
Okay.
I'll certainly do that by the time of our meeting.